To everybody, so good morning. And so today I'm trying to actually to push. I mean, something that in general is told in 60 hours course and in 45 minutes. So this means that we cannot do any proof. This leverage are very elementary concepts. So this talk is about very general things that could interest you. Because you're interested, you have to go through reference and books and so on and so forth. So many-body perturbation theory actually is a long history, starting from 40s, 30s, and actually it is a son conceptually of high energy physics. So quantum dynamics and the quantum fields have been introduced to quantum dynamics, and then people start applying to condensed matter. So this means that there is a complex, say galaxy of methods that you can actually that deals with the problem of many-body, and they range from density functional theory up to non-equilibrium density function theory, and there are different. There is of course an increasing complexity in mathematical terms, but what is important is that you have to pick up the method that gives the object you're interested in. So, for example, if you're interested in time phenomena, you have to move to the top of the tower of complexity. Because up to what we do today, what is GW about, and it's not about time. You will see that we try to multiply now time with the body is meaningless. So if you want if you're interested in real-time phenomena, you cannot use GW. You use different methods, so different tools. And so today we will actually discuss briefly about many-body, and we will stay, and then I'll show you how time is meaningless. But if you want to reduce time, you have to go up in the tower, in the complexity. And actually, what to use depends on what you're interested in. So if you want to calculate band gaps, of course, because Adam has been talking about it. So you need density function theory. If you have something that you can interpret as a gap, then normally you should do it because there are not really sufficient energies. But yeah, you can use it. Then you can use many-body to correct the gap, and then in that case, GW is a reasonable approach within some constraints. Then if you want to calculate absorption, well, in that case, you have many-body, but also TDDFT can provide absorption. And already, if you want to go to strong already materials, so the materials where you have a strong on-site interaction that is modeled like other models, well, in that case, GW doesn't work. Because GW is an approximation that is designed to work in a regime where the electric properties are dominant. So the electrics is not so important, but short range and on-site interactions are important. Well, in that case, you have to devise different approximations within many-body. Many-body can still work in these cases, even if you are the border of many-body, the border of the perturbation theory. So you see that, physics is very complex, it's very rich, and there is not one unique method that you can use to calculate everything. And of course, if you want to calculate real-time process, where this is really time, seconds, you see here you have energy, here you have energy, and here you have energy. Energy. Time, you have to use non-equilibrium function. That is an extension of many-body in a real time. Okay, so that line. First, I would like to introduce a concept that sometimes is a little bit hidden in the market. That is the Hamiltonian. We have seen yesterday that the Hamiltonian is used in our everyday life as a condensed matter physicist is the one with column interaction. Where is the column interaction coming from? And then actually we will see how the Hamiltonian that we use every day is not so formally accurate actually. Then we will introduce very basic concept of perturbation theory, and we will introduce propagators. Okay, propagators is something that in general, if you do many-body course, takes pretty much 6 hours. And today we use a shortcut, and using the Lippmann-Schwinger approach. The Lippmann-Schwinger is a very simple approximation to the concept of real-time dynamics at equilibrium that introduces, the concept of propagators. Then we will discuss about Feynman diagrams and briefly the zoo of many-body approximations. Okay, so what is the Newtonian that we use every day? So maybe some people did professional master in high energy physics. So you should know that in high energy physics there is no common charge. If you go back to your studies at the university in the quantum field theory book, there is no common charge. It's not there. Actually, the Newtonian or the Lagrangian that use QED is very simple. You can get very compact, especially if you use Minkowski notation, relativistic notation. It's very simple. And interaction is something like this. Very simple. Where this is time and space in Minkowski notation. And this is the rapid Newtonian. Then actually there is a procedure that has been introduced by Fermi in 1932. That is a way to rewrite this interaction in the column gauge. So you fix the gauge and then you manipulate. The manipulation that Fermi introduced is using Maxwell. So at a certain point, you forget that you're using quantum fields, that everything in the world is quantized, and photons, and blah, blah, blah. You forget it, and you say, okay, let me use Maxwell equation. And then if you Maxwell equation, then in this case, you see that there is this current interacting with the potential. Now, the potential, if you write Maxwell equation in terms of potentials, you have D'Alembert, blah, 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 the motion waves. Well, the solution, at least for the longitudinal of this object, that is distinguished from the transverse because of the column gauge, well, this longitudinal component of the potential produces the column interaction. So this is just the solution of Poisson. This is a classical potential. So you see that when we introduce the Newtonian, we use every day, we do a trick. We're fully quantistic, we go temporally classical, and then we go back quantistic. This is how the Newtonian method, this is the one that we use every day. The column interaction. And this is the object that makes many bodies important, because many body is designed to solve the problem with this interaction. But it is important to keep in mind that there is a trick when you do condensed matter, and you're not completely formally consistent with the QED. Not relativistic, we are not relativistic regime. Okay, no relativistic. What you would like to do is to derive your low energy Newtonian from the low energy expansion. And this at the moment is not what we do every day. We use a semi-classical approach. So the Newtonian we use at the beginning is semi-classical. So you say, okay, then I have classical physics with Maxwell, I have quantum physics with QED. QED is in charge of quantistic. There is no classical part of the QED. And then you have many body. So many body is in the middle. Many body means with a leg in classical mechanics and a leg in quantum mechanics. And this creates a lot of confusion. We don't have time today, but we could do a lecture about the confusion that is created in the literature. So you can see that some of our colleagues are not very clear about this distinction between classical mechanics, quantum mechanics, and it's produced a lot of misinterpretations. Okay, so many body. So if we accept the Fermi Newtonian, so this is the Fermi Newtonian, so to give credits to our one of our most important Italian physicists. So this is the Newtonian, and then we have to solve it. So how do we do it? The situation is really complicated because in general, the only way you have to deal with this kind of problems is to think in terms of one balance, right? Maybe that we want to study dynamics of this room. So the simplest thing you can think in terms of single persons moving. So this picture is very sound, very simple, because we can imagine that we can have excitations where one is in the bathroom leaving an empty chair. It's very simple. I mean, it's very intuitive, but it's very far from the reality at the end, because you know that there is an interaction that is connecting each of you. You can think this as a as a rope connecting. Then this means that the guy that goes to the bathroom has to take with him other people, because there is actually an interaction that is connecting the different persons. And this interaction, because nature is what makes life complicated to humans, and this interaction is long range, so it does not decay exponentially. And this is actually the source of a lot of implications, but also a lot of physics. Okay, so so if you ignore the interaction, the problem is simple. You have just that your ground state is just a product of free particles, you know, piled with the energy. Very simple. You can write any observable analytically. Simple, just simple. I mean, DFT is this. Then what happens with many body? So what is the goal of many body? What would you like to do? So the goal of many body is to replace this fully interacting object with a non-interacting or weakly interacting gas of something, where this something are indeed quasi-particles. So this is the goal of many body. And this is, for example, one of the most known applications of this concept is the Landau-Fermi liquid theory. So in the theory of Fermi liquids based on the quasi-particle concept. So you actually demonstrated in low energy case, you can replace the particles. So this means that you replace the bare person in this room with something different, dressed, put jacket, you put something. So this dressing makes in such a way that the residual interaction is weak. And this is the concept of, and this is the final goal of many body actually. And GW is indeed one of the strategies used by many body to arrive to this picture. Okay, so at this point we can already draw parallels. We will do it more in the lecture, but at this time we can already draw parallel with this functional theory. So in density functional theory, you are interested in the ground state density. So then I did talk yesterday. She made clear that in DFT, the only thing that you can hope to calculate exactly is the density, nothing else except the density. Then you can use current density functional theory to calculate the current, but in general, you have absolute excitation. And with many bodies, that what you have is that the many body approach using what we will introduce as the grammatic expansion will rewrite the problem in another effective problem with the same excitation spectrum. So you see, same ground state density, same excitation spectrum. So from many body point of view, many body, the Cornish-Shum density functional theory is a mean field plus particle approximation. So very, very simple, very limited. But I mean, the goal is completely different. I mean, many body can calculate total energies, but this is not the main goal of many body. Okay, so Lippmann-Schwinger. Schrödinger equation is, you should all know, Schrödinger equation is a quantum mechanics basic equation, as describing with this time the evolution of any state of the reaction. You see, the Hamiltonian, that's H0 plus V, is not, sorry, here's a missing piece. So it's not time dependent, but still with Schrödinger equation, you introduce a fictitious time, because you know better than me that if you are in the latent state of the Hamiltonian, you're simply just oscillating with just a simple exponential. But this means that you can rewrite normally the Schrödinger equation in time with this expression. Now, at this point, to treat the effect of V, because V is the monster, thing that you don't know. I mean, in many body, V can be several things. It can be the electron interaction, but you can apply the entire many body scheme to calculate any kind of interaction. It can be a spin orbit, it can be electron quantum, it can be magnetic fields, it can be spin-spin interaction, it can be anything. I mean, it's an approach to calculate dynamically the effect of a perturbation. But at this point, once you are at this stage, where now for the moment for the next slides B will be one body, one possibility is to use rather Schrödinger perturbation theory. Another that is not so known but is very famous is the Feynman path integrals. So it is another exact way to solve the Schrödinger equation. And then there is Lippmann-Schwinger quantum propagation. What is that? So Lippmann-Schwinger, you can rewrite this equation. You see, this is the interdifferential equation. And then you can first solve the homogeneous part. And if you solve this homogeneous part, you introduce this operator, that is the the propagator operator, this object, that is just solution of this. Then, I mean, it's a matter of simple math to show that the solution of Schrödinger can be rewritten in terms of this propagator, you see? So this is how you solve interdifferential equations. In general, you use Green's function. You consider the homogeneous part that you can solve, you define the Green's function, and then in terms of this Green's function, you solve the full problem. At that point, you have a self-consistent problem, so you have to do approximations, but you can formally provide the problem exactly. What is important here? You see now the time that is, again, is very trivial. So you have to remember that time in Schrödinger is really trivial. I mean, so you know that in this is squared. So psi of t is e to the minus e t divided by h bar psi 0. This is just trivial. This the time evolution in sorry. So the time evolution in Schrödinger is trivial. The point is that the energy there, the energy is the full energy of the full Hamiltonian that you don't know. It's unknown. So the object, the dependence is trivial, but the energy you don't know. So the trick of Schrödinger is to say, okay, I don't know the energy, I transform in time. You see this time derivative. The time derivative will just take down E. And then you say, okay, at this time, now I can rewrite in terms of this evolution. So, and this object can be solved self-consistently. So you see psi on the left, psi on the right. If you do it, you will see that the rewriting using this is Schwinger, this is Lippmann-Schwinger, this is Schrödinger. So all black and white, yes, the 50s. I mean, Lippmann-Schwinger is 50 something. And so you have here the potential. So you are evolving, first click, second click, and so on and so forth. You see this object here. You see psi on the left. So here, for example, if psi is equal to psi minus infinity, you have 4 points. So you do this scattering, and then this means that by using this scattering, you can rewrite different orders. You see, this is first order, you have the second order, and so on and so forth. You see, so this is the first part, then this is the second part, and then you have binary orders, depends on B, right? Now, if you collect on one side, you take a part B, you have G naught plus G naught B G plus G naught B G V G naught, and so on and so forth. This series defines exactly the dress G. So you can rewrite all these dynamics in terms of G naught per dynamics, moving from one interaction point to the other interaction point, or you can actually replace everything with a full propagator that is dressed with respect to G naught. So at the end of this manipulation, I mean, we are doing everything with one body potential. So the one body potential V is trivial. I mean, actually, this is something that we could have done perfectly using Van Schrödinger. But the technique is much more general, because now you know that the problem of the energy, knowing the energy of a steady Hamiltonian is transferred to what? To the Green's function. So if I know this object, this operator is not functional, this Green operator is a propagator operator. If I know it, then I have solved exactly the problem. Without analyzing, I never calculated the eigenkets of the negative states of the Hamiltonian. So this rewriting of the Schrödinger problem, the many body problem, steady state problem, in an effort in time evolution, this is the core of main body. This is really the most important aspect of many bodies. It is in common also with TD connection, with TD DFT, and with non-equilibrium function. Now, in all these methods, you forget about the eigenstate problem, to solve the Hamiltonian problem, because it's too complicated, and you transform the problem in a time evolution. So this means conceptually that, but it's something that is taught in quantum mechanics, that if you want to calculate the dynamics of this mean of you all interacting, then one way is to look about the eigenkets of the dynamics. but it's n body problem, super complicated. The other end is formally equivalent. If you can describe what is the position probability of one of you to go from here to baffled, you have solved exactly the problem. Okay? It's probably equivalent. Right, so this means that once you have this propagators, actually they have a physical intuitive interpretation. If you calculate the average of this operator between two space points, space cats, then you have a function. This is the Green's function, and this is just the probability that the system will move from this point of space-time to this point of space-time. So this is a Green's function. Now, then there is technically the problem of ordering, pseudo-time, and blah, blah, blah. But conceptually, what you are calculating is the probability of the system to move one point of space-time to another point of space-time. If you are able to calculate exactly this probability, then you win. You know exactly the solution of the problem. Now, to go from here to Fermat diagrams, there is a bunch of math to do. Because clearly now this is very simple, very intuitive. But how you go from here to Fermat diagrams, you need a math that we will not do it. But what we can do at the moment is just intuitively to see what happens. So now the density. This is the density. This is the average of an operator. You see, it's very similar to the. You see, it's very similar to this object, right? So the density is actually the average of an object like this in the same point of space. It could be also psi w r of t, psi r of t. So the density just corresponds to the evolution of the system into itself. This is the density. But when you look at the density from the Liebman-Schwinger perspective, you just realize that it's just a Green's function where you started and you went back to the original point. Now, this object actually, we know how to calculate it. We know that we can calculate it if interaction is weak using Kubo. So we don't need all the many body. So with Kubo, you can calculate exactly the interaction, the density, the density plus the integral the response function. So not even there's nothing to do for that. So in Kubo, you can calculate this often. Say, how can I find again this result using all the machinery that we are? Well, this Kubo, so as another more physical message, that is the fact that when you perturb the system with a potential V, this potential is one body, then at the lowest order interaction, the system creates this polarization. So what is this polarization? Okay, the polarization, in order to understand what is this polarization, you have to do a little bit of step forward by using second quantization, that is Dirac notation. And then you remember the average of psi w psi is the Liebman-Schwinger propagator. Is the object, and if I know exactly the problem here. This is the average of psi w psi. We introduced just before, right? So now, if you look at this term, if you look at this propagator and you remember that Green's function is this object, then you can say, okay, wait a second. This object there are psi w psi because the density psi w psi. Now you have psi w psi. Well, there are two, right? Psi w psi, psi w 2. Then, if I want to write this in terms of Green's function, I will have a first that is psi w psi, and then another psi w psi. So this means two Green's functions. So this object can be represented as, in terms of Liebman-Schwinger, as this dynamics from this point to this point, and back from this point to this point. This is the response function. And this response function, when we introduce the Liebman-Schwinger operator, can be rewritten indeed in terms of propagators. Now, this is very nice. This means that actually it makes you intuitively understand that even whatever you produce with Kubo or even with TDFT can be rewritten within many body using Green's functions. But now we miss a piece of the many body PT, perturbation theory. because at the moment we didn't discuss about the role of perturbation. And then to do the jump and to introduce formal many-body perturbation theory, we need a key theorem that actually is very instructive. So this is the only theorem that I will not prove, but we'll just talk about. So how you do in many-body? So in many-body perturbation theory, still you have to calculate the density. Then you use a different path. You say, now this psi of t is my ground state, time-dependent ground state. It is evolved from a certain initial point using the evolution operator. Then you send the initial point to minus infinity, and then you do the adiabatic hypothesis. The adiabatic hypothesis is a cornerstone of zero temperature many-body. But it's very instructive because it is the proof, the formal proof that time is meaningless many-body. In the adiabatic instance, what you do is that, so you want to use the streak, right? You want to go from minus infinity to t. Now the point is that when you calculate this density, you need to put inside some ingredient of the first ingredient, the one without interruption, because otherwise, how do you do it? So you need to get rid, at least when t equals minus infinity, of the interruption. So with the adiabatic hypothesis, you assume that the interaction is switched on adiabatically, very slowly, and then it is switched off adiabatically. So you switch on adiabatically and then you switch on off adiabatically. By using this trick, the u on the left and on the right can connect this density to the non-interacting state. This is the basis and is the proof that you can actually, the proof that when you send the adiabatic switch on 0, so when you do, when there's a parameter, when this parameter is 0, you remove the adiabatic switch on. The proof that in this limit you get the exact solution is the Gelman-Law theorem. Gelman-Law theorem is a cornerstone of many-body and makes clear that time in many-body has no link with real time. Okay, then this is just a few technical so you want to solve the equation of motion for the evolution operator. Then you provide evolution operator as the bare evolution operator and an operator f. Now this clearly we did everything very quickly, but this u naught is very much g. It's very much, so you see again pretty much entering in the story. So if you do this and then you solve f, you know that f can be formally written as a series with a constraint ammeter because the operators speed, they don't communicate with each other. Now, this is the expansion of an exponential because the evolution operators in quantum mechanics are exponential. So you do evolution of exponential. This series is the perturbative answer. So you assume that B is such that this series converges. So this is your another cornerstone of many-body. Okay. So one is that you switch on binary. The other is that you assume that interaction such that can be expanded perturbatively. And so, for example, if you consider another model with a strong one-side interaction, no, it does not converge. If it doesn't converge, you cannot use perturbation theory. You can use fundamentality. Strong. So you say in the literature, in the cases I'm interested in, it always converges. But it depends on what you're interested in. I don't know. Okay, so then you can actually apply the evolution operator on the left and the right of your density. Again, you use the same trick. And then you have that in terms of Green's function, this object will produce exactly what is in Lippmann-Schwinger. So free evolution with one scattering, with two scattering, so on and so forth. Then you put everything together. So the left and the right, the left and the right. So the left and the right, this is again pretty much Lippmann-Schwinger. So the interaction will make from minus, you remember Lippmann-Schwinger, so it was a scattering, but minus infinity to t was going through a lot of scatterings in the middle. So this is exactly Lippmann-Schwinger. On the left, Lippmann-Schwinger on the right, you have to connect the one on the two, and you get that you have one evolution that is free, one evolution with one scattering, with two scattering, so on and so forth. So this description that is actually the extension of Lippmann-Schwinger to the full problem is Dirac equation. So the Dirac equation is just a way to rewrite the Green's function in terms of the Berglin's function and the interaction. Again, this is very much like Lippmann-Schwinger. So the simplest way, simple time rewriting of Schrödinger equation. Just that to make it formally, to write formally on top of a general interaction, you need a few of mathematical inputs, of which Gallman-Low theorem is one, and also the interaction picture. I mean, there are a lot of small details to do it formally. But at the end of the day, you are solving the problem in terms of Green's functions. Then now it's nice to see whether this object reproduces Kubo. Well, you can prove that yes, it reproduces Kubo because now the density corresponds to this evolution geometrically reconnected to itself. So this is the Baire interaction, and this is the first order. The first order is when you take these two extremes and you close in the same point. And then you get this down, but this is Kubo. So Kubo is just corresponds to the first order expansions of the density using Green's functions. Then if you go beyond, you have nonlinear trains. So this is Kubo. So say, in many bodies, you can obtain the Kubo quite easily at the first order in perturbation theory. Okay, so key messages. Many-body is based on semi-classical definition of the interactions. This makes the many-body from a formal point of view much difficult to study compared to QED. May appear difficult, but look at, I mean, just to convince yourself, just take any book about electron-nuclear interaction with electron-nuclear interaction, look at the Hamiltonian. The Hamiltonian generally takes 3 lines of the paper to write. I mean, it's lots like this. Then go and search for the most complicated QED Hamiltonian, written in Minkowski notation. Just kind of small. So the point is the complication. The fact that the Hamiltonian is very complicated is because it is the result of a semi-classical manipulation. Then many-body is actually a way to rewrite a many-body problem as a propagation on a pseudo-time, because the time in many-body is not in real time, under the action of slowly winding potential. So, I mean, many-body is very much limited. You have to be careful. Body is valid within certain approximations that are valid, that are there even for the exact solution. So, Chigapa in particular, Chigapa has more approximation at top. But if an interaction is strong, no GW, but no any other energy. If you are interested in the time dependent phenomena, so you want to do an experimentally simulate, comes to say, oh, I measure, apply the field and measure a time dependent charge oscillation. You say, no, I cannot calculate with that. So I have to find different method. Then diagrams actually, we will have some time now, maybe, but diagrams allows, and this is the fortune of Feynman, right? Richard Feynman. I think that when a few years ago there was even a comic about Richard Feynman. Yeah, I give it to my kids. It's drawings and diagrams and blah blah blah. It's very nice. I mean, the way to write and why so was successful was because he managed, apart from the path integral, and I think from my point of view is the most impressive result of Richard Feynman, path integral. But in the diagrams, it makes a fortune of Feynman because you can provide a very super complicated problem geometrically. So you can do drawings that, thanks to rules, correspond to equations. But you can do manipulations graphically. This is the Feynman diagram. And time does not correspond to real time. So to even convince yourself, it's enough that you look at the first chapter of the formalism of finite temperature. To go finite temperature, from there you have to use the Matsubara formalism, where time becomes imaginary. So, bye-bye. I mean, the Green's function even periodic in time. So, nothing to do with real time. Okay, so now you say, okay, this is very nice, but then I want to do calculations. How do I do it? Well, situation is not so simple. Why is it so complicated? Because now, of course, the interaction we're interested in is not one body, but it's two bodies, the column interaction. Now, you can repeat everything with the column interaction, but you have complications. Why is that? Because now, if you look at the of this object, you know that this density upside down psi, this is upside down psi, so you have upside down psi, upside down psi, and you have this one r minus r prime between. So this means that the basic scattering potential with the electron interaction is not a one-body object, is like a dot where you have something entering, something out. No, it's not. You have in general 4 bodies involved. You see, 4. 1, 2, 3, 4. So this means that you can again apply, because all the machinery you have designed is for the density. If you go back to the slides, previous slides, we never assume a one-body potential, except when we do darkness, when we said, okay, that's the next Riemann-Schwinger. When you connect Riemann-Schwinger, we use a one-body, but the derivations, I mean, Gell-Mann law, and also the Gell-Mann rules, everything is independent of potential. It can be even free-body potential. Actually, free-body potential will not conserve a number of bodies. So 4-body potential, 6-body potential, can be spin-spin, can be, I don't know, electron spin, can be any interaction. The point is that when you go to write the elemental scattering processes, you have a problem, because instead of having something like this, now you have something like this. So the action of V will produce one scattering plus 2 new bodies. So this means, in terms of you in this room, that one-body potential means scattering of one of you has to open the door, right? So to open the door has to open the door. This is the interaction. Open the door, close the door. But it's simple, because this guy will eat, go. The column interaction instead with this, that, very complicated. So you have this guy wants to go to the bathroom. Okay, now the guy will stand up and go through the other door. Okay? So the first guy will go to the bathroom. The second guy, well, the second guy can actually go here, scatter with the door, and go back to where the first guy was sitting. Okay? And now there is an empty seat there. So this is exactly the column interaction. Column interaction is something that involves 2 bodies at the same time, 4 bodies, because you can imagine that this guy eating the door will turn another person outside the door, and the same guy, same story with the other one. So this means that at the end, now this is first order, right? This is first order. Then you go second order, means another guy will stand up. So this means that if at the end of the first process I have 2 persons that I don't know where they are going, at the second order I have 4 persons I don't know where they are going, and so on and so forth. So this means that the column interaction produces an abundance of bodies doing the interaction, an abundance. And then you will see in a minute what is the concept. Because now, if we go to the first order, where now the interaction is not B, it's not the one body. Remember, it was first just a dot here. Now it's the column interaction. You have you on the left producing this, you on the right producing this, but now you have to join together those 2. And now this is why you are talking about Feynman. Because this is like even a kid can do it, right? You need to connect the lines, you need to connect the arrows, so that you have an arrow that is getting out to connect to one that is incoming. And then you can do it in, I mean, the lowest order, you have one option only. So when you connect this to this, you have to close this way. You see, close this way. When you have to go from here to here, you can actually connect, instead of this going here, you can connect this going here. This, and then this goes like this. Now, if you do this, the lowest order interaction, you get the free propagator, the Archie potential, and the Fock potential. So this is Archie Fock. So Archie Fock is what you get from anybody at the lowest energy interaction. So you get for the density, and you get Archie Fock for the Green's function. And so this is Archie Fock. And then you see that you can actually, Archie Fock becomes an expression for the, you see that you have evolution, then you have evolution, scattering, evolution. Evolution, scattering, you see all this object here between this point and this point, you can define it to be this sphere here. So because this becomes G plus G, V, G sigma G. Exactly like Riemann-Schwinger. Riemann-Schwinger we have G naught plus G naught, V G naught. Here we have G naught plus G naught, sigma G naught. What is the difference between Schwinger? That V now turns in a no local space and time object, This is the self-energy. And the lowest order is Hartree-Fock. That is, in the case of Hartree-Fock, time independent. But if you go already to the next order, you have Hartree-Fock plus those two diagrams. You see, I'm connecting this with this. If I connect this with this, I get this object that is the second order contribution to the self-energy. So beyond Hartree-Fock, those are the lowest orders. So if you consider those two terms, you have the Born approximation that is perfectly consistent with Lippmann-Schwinger. So Lippmann-Schwinger is really enlightening theory that you can do to understand before you start with many body. So Born approximation and many body becomes the lowest order, lowest second order approximation, and you get this. Now, you say, okay, this is very nice, but then how do I do it general? To do it general, well, you need a series of tricks that are grouped in the diagrammatic rules. So in the diagrammatic rules, with one key rule, I always say because I'm very patriotic. So one big rule was played by an Italian, Giancarlo Mick. There is in the derivation of anybody a step where you end up with a very complicated object. You have an average of a T product of a lot of variables. How to rewrite this in terms of Green's function? This is the Wick's theorem. And this theorem is a way that you can actually introduce these elemental objects that are Feynman diagrams, which are Feynman and Giancarlo Wick. Now, this is very nice. Then you say, okay, now, so at the end of the day, assuming that the perturbation theory holds, assuming that you are happy with Gell-Mann law, assuming that you don't care about time and you are just interested in on excitation energies, so okay. The self-energy, what about the self-energy? You have a problem, right? You have the problem is that already at the second order, you have two diagrams, but at the third order, you have 18 diagrams. The fourth order, you have 64 or something like that. You have a number of diagrams that explode exponentially. And then how do you do it? The story is complicated in the sense that you have then to select which diagrams. And this is something that, I mean, an high energy physicist will love you. Because of course, in high energy, you have not even one field only, you have different field, different interaction. You have strong interactions. And indeed, if you go up to purity in general perturbation theory, is not the best strategy to use the organization group. But we are in smarter, we assume we are safe, we want to be safe, we judge, blah, blah, blah. So we need to decide which diagrams to sum. And this is part of the story. And this is actually something that have been studied by a lot of colleagues starting from the 60s, 70s, 80s, and so on and so forth. So how do you decide which diagrams? There you have an L, and then I think that the spin human body is really beautiful. You have an L from what we thought at the beginning was a problem. I told at the beginning, oh, natural was make things complicated because the column interaction is one way up. This means that if you Fourier transform, because like one over Q squared, it diverges in the long wavelength limit. But then you, thanks to this, actually, in the case of the high density regime, you can prove that there are certain families of diagrams that are dominant because they diverge. They diverge. Thanks to the column interaction. So in the high density limit, you have an exact solution because you have a family of diagrams that are divergent and dominant. This is GW. GW is the high density regime. But, you know, high density. So what about the other regimes? Well, there you have two extreme cases, or some extreme cases, where you know exactly what are the most important diagrams. Another one is the T-matrix approximation, when you have said that the bodies are interacting in short range. So when they are very near each other. In this case also, you have an exact solution of the many-body problem that is through short-range interactions. But then you have a literature. You have a literature. So clearly you say, how do I do it? This is tricky. We can discuss it at a certain point. I mean, how you select which is the approximation that better fits your needs? Well, at the moment, we have more validation results. In the sense, you apply something and you check. Because from a formal theoretical point of view, we don't have too many, certain points. I mean, from a formal point of view, I can't say that Chicago works in titanium oxide, or in magnesium oxide, or in copper, or in germanium. I don't know. I don't have a proof. To prove it, you should prove that the diagrams that you have ignored are tiny. But this is a super difficult problem. And except in few cases, we don't have very clear mathematical proof. We have more if you go on the other side. There are in some cases of many body, some regions where you have mathematical proof and also benchmarks. But in the case of a complex material, it can be a surface or nanostructure. There we have, yes, then we have validation. We have, literally, GR has been applied for 50 years and it's reasonably result, but it doesn't mean that it's going to work in your system. Okay, then the GW approximation. So GW approximation is high density limit. So in the high density limit, you can prove that the bubble diagrams, they are all divergent. All terms here are divergent. Each of this is divergent. One Q goes to 0 with different powers of Q. And then the result is that, and this is also beautiful fact of nature, that if you sum all of them, they are not divergent. You can regularize, but this is also known in 3D, regularization. So you can include a certain family of diagrams, the individual are divergent, but some of them are regular. And this is the GW approximation. And the GW approximation indeed corrects the gap of LDA, except in some cases, you see MGO or CRO, so there are systems where it doesn't produce the right physics, because again, the physics of GW is the assumption that one is the G. What does it mean? Right in the G, it means, imagine that in this room, we have other 50% in the room, right? At the point where you are path, you can just stand up, or when you're in a concert, right? When you go to a concert, right? You are in the bottom right, with a lot of people packed together. If you want to go to the bathroom, wait, right? You have to go to the floor. The only thing that you can do in that case is, what do you do in general? You put the mover forward, like this, You can just oscillate, right? It's the only thing you can do if you're packed together. This is the high density regime. If you have the high density regime, the only thing you can do is to oscillate together. Say, okay, oh guys, let's oscillate on right or left. This is a charge oscillation. And when you are in high density regime, only charge oscillations are important, and charge oscillations are described by this diagram. So that's why GW works. But then you have also another case where instead of bubble diagrams that are connected to the electric properties, you have like earth spheres interaction. And in that sphere interaction in the low density. So imagine there are just few people inside this room, and they can interact only when they are really near each other. And a very strong drive, almost classical scattering. In that case also, thanks to the work of Galitsky and Hubbard, this is the only guy to cover. I think Hubbard is still alive. No, okay. Well, okay, this is by Steven Kohler. Galitsky instead is a Russian. So in this case, you can prove that the dominant diagrams have a different geometry, and those are the ones that lead to thematic approximation. And that is an approximation to the Hubbard solution. So we have Hubbard bands and so on and so forth. Okay, so take home message of this section is that many bodies in exactly steady state theory. In many bodies, you take into full account no longer process partially and temporarily. And from many body perspective, DFT is a mean field approximation. The price to pay is that the complexity grows enormously exponentially with the perturbed body order, grows exponentially with the kind of interaction because it's a perturbation here. So this means that you have an infinite number of diagrams, and you have an infinite number of families of diagrams. So you can group, so that's super complicated. They are numerable, but infinite. So this means that you can also group them a different way, but the different way you can group us still infinite. So it's really complicated. And but thanks to God, there are some approximations. There is lots of theory. So there's just 2 books. There are many books. And then also on the Yammer webpage, you can find selective readings. Okay, thanks for you.
Yeah. Much time. Running late already. Yes. That's good.
So if the starting point of any body perturbation theory is a non-exceptional system, a non-interacting system on the area, then how can we take that into GW approximation? Can we ever deal with material point of view, heterostructure systems in the many body perturbation theory?
So you mean how to do also this machinery on top of DFT?
DFT is the starting point.
Well, in this case, in my lecture, DFT is not a starting point. No. But you mean, how do you extend all this to when you want to start in DFT, not start from,
Yes, and especially for heterostructure systems, we have
Or-
many heterostructures.
Oh, but I think the problem is general. The problem is that how do you run GW or make by or have one images on top of DFT? So, yeah, this is itself a big problem because for electrons, I think you can take a lecture on this. I mean, many body is full of technical details are potentially traps, potentially points where you need to be very careful. So when you do dense functional theory, from many by point of view, you're doing mean field. Mean field means that you have introduced some level of interaction in your system. In order to avoid double counting, what is double counting? Imagine that you are introduced some process that let's forget about it. Imagine you actually fall. Right? With one specific you actually fall, right? Imagine that you did after fall, you want to do GW. GW needs to remove actual fault. So he has to say, okay, I have to start from actual fault. I can do it, but I need to remove actual fault from my self-energy and recalculate the differential. You have to remove the initial potential you have introduced and add this differential, because if you don't do it, you will introduce actual fault twice. With the FTF, same problem. You have first to remove the exchange correlation effects that are embodied in FT and then add GW. This is what is done in Yaml. In most of the cases, it is simple, but not always. Because, for example, if the FT uses FTA plus U, well, in that case, the potential is not a simple potential that you can. So it's not of the families of local densities potential. So in that case, you need to code with the code, then tell to the code, give me the class U interaction. Then you have to remove it and add it on. If you go to other fields, other interaction like the electron column, there is still an open issue how to correctly and formally merge together many body and DFT. There is still an open issue.